Dan Olds here, and we are at our first stop in the 2022 Great American Supercomputing Road Trip. We are at Pacific Northwest Laboratories, and we are talking to Robert. Robert, tell us a little bit about yourself.
Good morning. My name is Robert Rallo, and I'm the Director in the Advanced Computing, Mathematics and Data Division in the Physical and Computational Science Directorate at Pacific Northwest, which is a division that mostly works on the computational mathematical aspects of scientific discovery.
That sounds a little bit complex, and you've got a complex job.
Yes. It's a complex job because when we are trying to use mathematical models, when we are trying to combine this with data, when we are trying to combine this with advanced computing, the approach is always complex, and we have to face, and we are facing a lot of challenges in order to make predictions, in order to make models that can be reliable and can be usable in different domains.
You know, there are a lot of people out there that probably aren't as familiar with this lab as they are with, say, Oak Ridge. Can you tell us a little bit about the lab and its mission?
Yeah, so PNNL is one of the 17 DOE labs. We are stewarded by Office of Science. We are a multi-program lab, and we are focused on scientific discovery, energy, and national security. These are the three main mission areas. And our directorate is in the physical and computational science, which is in the scientific discovery space.
Can you tell us a little bit about what kind of compute resources you have here?
We have access, of course, to all the supercomputing resources that DOE provides for all the labs that are in the leadership computing facilities, but we are also hosting a mid-sized computing system and also different testing platforms that allows us to explore the scalability and the deployment of different types of algorithms in different types of hardware and different types of computing architectures.
And then you use the big labs when you need to scale up the big systems.
That's correct. Yeah.
Okay, that makes a lot of sense. Are you doing anything with hybrid computing here, with anything that's on the public cloud?
PNNL is one of the, I would say, one of the pioneering labs in the integration of cloud computing with on-premise HPC computing. So we have a strong partnership with most of the cloud providers, with Amazon, with Google, with Azure, and we are developing for different sponsors a lot of applications that are leveraging this type of hybrid deployments, in which we leverage on-premise computing together with on-demand cloud resources through this high-speed connection that we have with several cloud providers.
Now, is that a matter of, for instance, researchers going out and grabbing a small cloud instance to sort of prove something out, or are you putting bigger jobs out there?
We are providing both, essentially, and it depends on the projects and it depends on the different tasks. So PNNL, through the agreements that we have with the different cloud providers, provides something that is called like birthright access to computing cloud resources. So each one of the PNNL staff have specific access to create their own instances in the cloud where they can do small experiments. And then we have also access to instantiate whatever size or whatever scale of computing systems that we need on the cloud or across different cloud systems.
Sure. Very good, very good. In your systems here, are you using accelerators like GPUs or FPGAs or anything like that?
Yes, that's correct. So we are focusing a lot on this space of heterogeneous computing, in which we are, for the nature of the work that we are doing in terms of simulation and modeling, we need oftentimes to scale the codes to these GPU architectures to get the specific acceleration or to meet the specific acceleration needs that we have. We also are working on the FPGA space by developing specific accelerators for specific types of workloads and workflows. And we are also working on spaces like quantum computing, neuromorphic computing, and other types of computing.
Do you see more accelerators in your future?
Yeah. More accelerators and more specific purpose accelerators. So a lot of our work is based on synthesizing the specific types of accelerators that can help us to really speed up very specific workflows or kernels of very specific workflows.
Okay. And how about machine learning? Is that something that's mixing in with all of your applications?
So I would say that machine learning is probably one of the driving forces in this evolution that the lab has had towards more heterogeneous computing. And essentially, deep learning is what is driving this need of having this more tight integration between data and computing, and having these more specific purpose type of accelerators that can help us with the deep learning workflows in order to accelerate and to achieve close to real-time type of performance in some data processing workloads that we have, especially when we are working close to instruments and when we are trying to connect these three different worlds of edge computing, HPC, and cloud computing. This design of a specific purpose accelerators plays an important role.
Okay, but also machine learning is working its way in there to help reduce the universe of variables that you have to brute force your way through.
Yeah, and machine learning is instrumental for all the work that we are doing nowadays, and this is one of the bases of really getting additional acceleration, which is not just based on the hardware, it's also based on the mathematical and modeling approach.
So are you going to SC22?
Unfortunately, I will not be able to attend, but most of the people in my division are going to be there, and you will be interviewing later on some of them.
Okay. Yeah. Well, you've got to have some representation there, so that's good.
We do.
Got to be at the table. So let me ask you kind of a imagination question. Imagine that you're talking to all of the HPC vendors right now at this moment. What do you need 3 years down the road? What do you want them to do? What do you want from them?
We need to have better ways of having this integration across classical HPC computing, data-driven machine learning, and cloud and edge computing. And the future is going in this direction. It's going in the convergence of all these different worlds. So we need to start rethinking on the high-performance computing, thinking on what is next, what is beyond exascale computing, and how we can achieve faster speeds, more deep integration across all these platforms, and how we can really leverage computing at all the scales.
I see. Now, speaking of exascale, is that anything that's in the cards or on the roadmap for PNNL?
As I said before, we have access to the exascale computers from DOE, but we do not have any exascale computing system per se here deployed at PNNL.
We should get you one. You guys would do some great things with it. And kind of talking about computing architectures, there's some new capabilities that are coming up with CXL and the chance to better match up the hardware resources with what the application needs. Is that something you're investigating?
This is something that, and you will hear more about this on some of the other interviews. So the high performance computing group within our division is focusing on a lot of these deep aspects of high performance computing and integration of high performance computing resources. So yeah, this is something.
So it's definitely on your radar. Yeah. Okay, great. Last question. What excites you about the future of supercomputing? Is there anything specific?
Are you asking supercomputing as a conference or supercomputing as a concept?
Oh, as a concept, not as a conference, as a concept.
Okay, so I think that what I would like to see in the future is this transition to something which is much more integrated, something that allows us to, in our specific space where we are working, to allows us to move closer to autonomy and closer to autonomous science in order to really have a tighter integration between the scientific instruments that we have and the computing resources, and to have all of these systems working seamless.
That's the dream.
Yep.
Well, thank you so much for your time, Robert. I'm looking forward to talking to the rest of your folks.
Excellent.
Thank you. Dan Olds here, and we're talking with Kevin Barker from PNNL. Hey, Kevin, how you doing today?
Good. How are you doing?
I'm good. Can you tell me a little bit about what you do for the lab?
Sure. So my primary role is I serve as the group lead for the high performance computing group. And we're a group of researchers that look at computer science to support DOE science missions, broadly. We're a group of about 30 staff, plus we have some postdocs and interns that bring us up to about 50 people. And we look at, everything from hardware design to system software, including compilers, programming models, performance modeling and analysis, software optimizations. It's a broad, diverse group of researchers that we have.
You're singing our song. This is great. Good stuff. Well, let's jump into that a little bit. And we just talked with Rob here, and he was telling us that you're doing some on-prem and also cloud as well. And I imagine you're at the nexus of trying to make that work seamlessly.
We are. So kind of the DOE, historically, scientific computing in the DOE has been on-prem, right? We have large facilities. We have the largest systems in the world. We've deployed some exascale computing systems now within the DOE. And so that's kind of been the bread and butter for DOE HPC for decades now. And that's starting to evolve. And, there's a lot of reasons for that. One of the reasons is that scientific computing is moving from strictly computation to now computation plus data, or computation plus data plus AI ML. And so, we're seeing a convergence of a lot of different modalities of computing. And so that's pushing us not only towards the cloud, but also edge computing as well. So it's really creating kind of a distributed, almost ubiquitous computing ecosystem that can support scientific computing writ large, not just the large scale numerical simulation that we've done traditionally. So,
Great stuff. And you brought up machine learning, so I'm going to jump to that. What are you doing in machine learning? How is that helping you guys accomplish the computational mission?
So a lot of physical phenomena that we want to study, we don't understand fully the laws that define it, right? So, certain areas we do. We have very well established physical laws, and we can simulate those laws using large scale computing, and that's kind of traditionally been HPC. But more and more, there are areas where perhaps we don't understand the laws fully, and so we look at data. And so a lot of that data comes from experiment, it might come from observation, it comes from various sources, but then machine learning can help us make sense of that data. And so it's kind of a data-driven scientific approach as opposed to a model-driven scientific approach. And that's why machine learning is having an impact in the scientific computing space.
Now, I would imagine if you're doing machine learning, you're probably fairly deep into heterogeneous computing. So
Very.
Great amount of accelerators there?
Very much, and not just ones that are, in the marketplace. So this is kind of an area of interest for me as the high performance computing group lead and the type of research that we do. Accelerators have had an impact on scientific computing now for a decade and a half. We've seen GPUs, make a lot of inroads. I was actually at Los Alamos National Lab when the first petascale machine was developed, Roadrunner. And so I worked heavily on
the Sony IBM, broadband, whatever the hell they made.
The Broadcom, the Power XL 8i accelerator.
Yes.
Which came out of the PlayStation architecture. So I was at...
I remember that so well. It's really funny. Quick story. That year, I was at Supercomputing. I think we were in Reno, not positive.
Reno was 07, I think. Yeah, so right around there.
Around there. It was the Supercomputing just after that, and I'm having a meeting with NVIDIA. And they've got a couple of workstations there, and they're going, well, the real way to do this is using GPUs. I said, well, like what's in my workstation at home? Yeah, and I said, no, because IBM just did this whole petascale thing with the cell BE chip. I think that's probably the way to go. They said, well, yeah, but that thing's extremely hard to program.
And it was.
I don't think it matters. Turns out, who was right, who was wrong? I was wrong.
Yeah, so, I think, the GPU really took off not only because of the hardware, but because of CUDA, right? They had the programming model that went with it. Yeah.
Yeah. And they fed that environment.
Yep. And IBM didn't have that. So when we were programming this cell, it was a nightmare. It really was a headache. But that was kind of the beginning of accelerators, right? In high performance computing was the Roadrunner. And then GPUs kind of took over. But now we have a lot of problems that, perhaps GPUs aren't the best solution for. And so, we're not only using accelerators that are in the marketplace like GPUs, or, we're starting to see things, we call them data flow accelerators from companies like Cerebrus or Samba Nova. And we have a deep relationship with Samba Nova. We have a relationship with GraphCore. So we're doing a lot of work in these, data flow accelerators. But we're also looking at really truly custom accelerators that we actually design as part of the U.S. government. And so there's U.S. government innovative computing research looking at accelerators. How do we design accelerators? The tools, to do design and synthesis. How do we integrate them into an ecosystem that might have third-party IP like RISC-V, and these types of things? How do we integrate with that? And so that's an area of very active research for us. And we kind of lump it under something we call hardware software co-design, where, we look at the requirements of the applications, we look at the requirements of the science that we want to do, and then how do we actually design computing systems, including hardware, to support those science drivers.
Now, that's a surprise to me. I didn't know that you were out designing your own accelerators as well. That is pretty cool. That's got to be fun.
Yeah, I think that's for me, and where I live at the lab, where I sit, and the research I do, that's probably the most exciting area right now. There's a movement in open source hardware. I mentioned RISC-V, integrating third-party IP into, perhaps integrating with silicon on a package or through something like a chiplet architecture. How do we integrate our ideas with existing ideas, existing IP? And that's an active area. We have a number of efforts ongoing that are kind of in that vein. And so that's a lot of activity for us and interest.
That is really neat. Going a little deeper into architectures, there's a lot of noise around now about like CXL and composable infrastructures. And to me, this has always made sense because, from my years of working at vendors and research, applications are lumpy. They take different amounts of things and they don't conform exactly to a two-way 256 gig memory system, right?
Yeah.
What do you think of the future of this? Do you see great things? To me, it seems inevitable.
Yeah, and CXL is actually, it's interesting you brought up CXL in particular, because we have some research activities around CXL and standing up some advanced architecture test beds using CXL to kind of explore exactly those ideas. I think, when I worked closely with teams that would procure large scale systems, the bottleneck was always the memory, right? Because you had to design for the worst case, right? And so it's like how much memory per core, and then you have GPUs, so how much memory, and you max everything out, and it costs a fortune. And so it's, this idea of elastic scalability is very appealing, right? Because you can put the memory where you need it, or you can put the compute where you need it. And if you don't need it, you don't have to buy it, and you can move it around. And so, and that goes back to the cloud.
Like network attached compute, network attached storage.
Yeah. And it goes back to the cloud discussion too, right? Because this is what clouds are really good at, is elastic scalability, right? And supercomputers are really bad at it. It's a fixed system. So, these things all kind of, I think, are highlighting the same trend, right? Where we want this elasticity and this composability. And so CXL is a technology that's really exciting to us. And we're working closely with people like Micron. We have an ongoing effort with Micron and exploring exactly those kinds of issues. So yeah, it's really interesting.
That is great. So, are you going to SC22?
I am only going virtually, but quite a few of my team are going.
Okay. Anything exciting that you're looking forward to seeing or hearing about there?
Quite a few things. I think, this is always where we might get a new shuffling the top 500. I don't know that we're going to see much activity in the top 5. Things have kind of come out over the summer. But in terms of, activities that PNNL is actually engaged in, we have a number of workshops that we're co-organizers for. One is long running. It's called IA Cubed. It's an architecture, algorithms, and applications for irregularity. So looking at irregular applications and algorithms and how do we support those with different architectures. We've been organizing that. I think this is the 12th or the 13th year we've had that workshop. So that's a long running one. And I think you might be talking with Vito Castellana later today. He's involved in the organization of that one. So, he probably has a lot more to share. I'm involved in one for security for high performance computing, and this is a brand new one. We are very interested in, and our sponsors are very interested in, now that we're looking at data-driven computation, how do we keep this data secure? How do we understand the integrity and the provenance of the data? And how do we follow that data end to end, so that we can have trust in the end of the pipeline, right? So that we know we're getting good results at the end because we can verify the data as it moves through the computational pipeline. So, we have this new one, security and HPC. And, just as an aside, one of my other hats here is I help lead a project called the Center for Advanced Technology Evaluation that's sponsored by the DOE Office of Science.
Oh, okay.
And we've been going for 7 years now, so it's a fairly long-running project. And the idea is that we look at computing technologies that might have an impact on DOE mission down the road, 5-10 years down the road. So, we're very interested in advanced test beds and standing up prototypes. And one of the metrics of interest that we're interested in now, in the past couple of years, we've added is security. So it's not just power or performance and power efficiency, but also security. And as we get tighter and tighter integration between the compute components, right? Where, we might have chiplets on a single silicon package or something like that. Mm-hmm. How do we ensure that, malicious processes might not be snooping on, ongoing computation, that we're not leaking data, that, what are the observables inside the architecture? And so that's becoming more of a first-class design constraint, right? It's not just about area or power or performance. Now we have security that we want to think about as well.
Doors, back doors.
Yeah, covert channels, side channel attacks, things like that. And so that we have a workshop on this now at SC this year, and so that'll be an exciting one to see as well.
Well, given what what you were just talking about in the last couple of questions, I think you're going to love this wrap-up question. Assume that you're talking to the entire HPC vendor community right now. What do you need from them in 3 years? What do you have to have go?
Well, that's a good question. I think that's a really good question. I think, we need to have an open ecosystem, something where we can have contributions from the labs and from academia. The hardware infrastructure has always been kind of a walled garden. It's like certain vendors own it and you kind of get what they give you. But I think, going forward, how do we collaborate with those vendors as opposed to just wait for the next product iteration? How can we insert our ideas or integrate our ideas in with what they're doing as well? And so I think, breaking down some of those walls over the next 3 years is going to be really important. And I also think, thinking about HPC outside of the facility, right? HPC is much larger than a machine room now and going forward. And so how do we integrate edge computing devices or sensors or scientific instruments with an existing HPC and cloud infrastructure, right? So what are the protocols we need to make that happen? How do we have security baked into the system, from the onset, not kind of grafted on as an afterthought? So how do we really move towards an integrated end-to-end distributed ecosystem as opposed to just everybody connects to a machine that sits in a machine room in a facility somewhere?
Good stuff. Good stuff. Thank you so much for the time, Kevin. Really appreciate it.
Oh, thank you. I enjoyed it.
So we have our third interviewee, or victim, however you want to put it, of my fumbling, muttering interview style here at Pacific Northwest National Labs. Introduce yourself, tell me what you do.
Yeah, hi Dan. My name is Mahantesh Halappanavar. I'm a computer scientist by training, and I also act as the group leader for the data sciences and machine intelligence within the Pacific Northwest National Laboratory.
So what kind of applications do you work with?
So our group sort of touches a broad set of applications. So in my own case, I do work a lot on the graph algorithms or combinatorial optimization problems. As you might have heard a little bit from other researchers, so graph algorithms sort of pose these irregular...
Graphs are hard.
They're very hard on computers, so unfortunately I have this job of trying to parallelize them, make them work on these really big supercomputers. And the motivation for us was in scientific computing. For example, when you try to solve a large system of linear equations that are very sparse, so you tend to have a lot of zeros. So you don't want to store them explicitly. So you build these very sparse data structures, and when you're trying to factorize them, you end up with having to pivot the rows, and that messes up with your data structures. So what you usually do is to model it as a graph, and then you run one of these graph algorithms. It could be, for example, weighted matching. Okay. And then that would ideally put these heavyweight elements on the diagonals, so you don't have to do these pivoting when you're actually factorizing during the runtime. So that means that your data structures can remain intact. But unfortunately for supercomputers, it's basically you go to the library, you bring a book, but you only read one line. And you have to go back to the library again. So there is not enough compute to amortize this cost of having to do the
go to the library.
Right.
That's a very good way to put it.
Yep. So these are extremely challenging. And since the beginning of my PhD thesis, back in the 2008 timeframe when we had the first generation of supercomputers, so we have been doing graph algorithms. And I also lead one of the exascale computing projects, co-design center on graph algorithms called Exagraph. So we have researchers from Lawrence Berkeley, Sandia National Laboratory, and Purdue University. So we have been putting graph algorithms to whatever we expected back then. We didn't really have a very good target, but we said we targeted accelerator platforms in a broader sense first, so whatever was available to us.
So accelerators help in graphs.
So that is the idea. But again, if you see why we should do it, right? So you have a large system of linear equations. It's already distributed on 10,000 nodes, right? So you don't want to bring them all back on one node.
No.
It might not even fit in the memory, or the memory movement cost is going to be very expensive. So graph algorithms, whether they really need these exascale computing platforms or not, you would really want to solve them in distributed context.
I see. Yeah,
so,
and to keep them in memory
to keep
as
them
much
in
as
memory.
possible.
Right.
Sure.
So that was our motivation in the very beginning.
Okay.
When we were looking at these highly, problems with very small computation in them, very few floating point operations like matching, like graph coloring and things like that. And what we have recently done is to look at these newer set of graph problems that are used quite a bit in analytics. For example, you could look at influence maximization. So you basically think about this from a viral perspective. So you have a social network and you want to, say, distribute a small set of places. So maybe we can go back. So maybe you have a big system of, say, for example, a water distribution system, and you want to distribute a small number of sensors on this so that you can have maximum visibility of your system. So where would you place these sensors? Because it takes cost to put these sensors and you want to optimize on that. So these tend to be graph problems that are also NP hard. That means the amount of compute you have to do is going to grow exponentially. So we can really benefit from accelerators. And what we did in our Exagraph project is we showed that we could actually bring down the runtime from, say, 8 hours with serial codes that was state of the art to under a minute, to about half a minute. So when we ran it on GPU platforms.
Really?
And when we ported it to Summit, from a Summit at the Oak Ridge National facility, so what we really observed is that we could actually solve problems a lot more accurately. as well as scale it up quite a bit. So we observed up to 790 times speed up when we were running them on Summit with 128 nodes.
And Summit has a greater GPU to CPU ratio.
Yep.
And what do you think, where do you see that going?
In fact, if we just take a step back, so one node of Summit has 6 GPUs.
Yeah.
And even if, say, we ignore the tremendous amount of CPU computing power, so it is already like a million-way concurrency just on one node.
Yeah.
And on the entire Summit system, it's 4.5 billion GPU threads that are available at any point of time. So this we have never thought. And so back in my PhD days, we thought about 16,000-way parallelism and 32-way 1,000 parallelism. But that was very neat, very homogeneous in that sense, in that we had CPU threads.
And that was it.
Like everything looked exactly the same. But now we have this weird hierarchy of computing power as well as memory.
Yes.
So we have warps, we have SMs, and we have GPUs, and then we have entire systems. And similarly, there are like 5 levels of memory hierarchy on a GPU and then CPU. So it is an extremely hard problem to load balance. It is an extremely hard problem to optimize for coalesced accesses.
Are you looking at different types of accelerators as well?
So we have looked at quite a few. So when we started the project, so the ones that were directly available to us were the NVIDIA GPUs. So we highly optimized them for NVIDIA GPUs because the software system was also really good. And now with Frontier posing us the AMD environment, so even though they are providing quite a few tools that we can take our codes and put them onto the new platform, it's not always straightforward.
No.
So our current focus is on trying to port our codes for the AMD platform, and we are expecting it that at some point we'll also have access to Aurora. So we'll have to port them to the yes. So it is turning out to be quite a bit of challenge, and we are trying to see how we should do it ideally. So one way would be to do it through OpenMP offloading, and there the vendors are still working on optimizing the compilers, and we are playing the waiting game just a little bit so that we don't have to invest a lot of time on very specific computing tools.
Now, there's some other things out there too. We just had an interview with Kevin Parker, and he mentioned GraphCore and Cerebras.
Yes.
And those are interesting, but I'm not sure if they're interesting for graph.
There have been few efforts at the PNNL that I'm not particularly aware of, exploring, trying to use Samba Nova for graph algorithms.
Yeah, that's right. Samba Nova you managed to. Yeah.
And the idea is that I was when I started my time at PNNL, we had access to Cray XMT supercomputer, which gave us a fine-grained control on very fine-grained control on how we could do graph algorithms. Right, so we could use these hardware threads for synchronization, and we could also use this very long instruction pipeline for tolerating latency. So this is something that's not really directly applicable to platforms like Samba Nova, which is coarse-grained.
Yeah.
And my colleague Vito will probably tell you a lot more from the hardware perspective.
Let me throw the greatest accelerator of them all at you. What about quantum?
Yes, I did spend a little bit of time looking at quantum. I think
mean, that could be really promising for graph.
It could be really promising for graphs, especially when we expose it as one big combinatorial problem. But I think it needs a fundamental shift.
Oh, really?
In our the way we design our algorithms.
Yeah, I think you're right. Have you gotten a chance to use any quantum simulators yet or anything?
No, I have not used them myself.
They're coming.
They are coming.
They're coming from major vendors.
Yep.
And you got to talk to one about getting a little under the covers look at them, because I think you're right that the algorithms are going to have to be changed.
Yes.
But it could be really promising for graph. It's one of the, I think quantum's pretty niche-y right now, and I think that graph might be in that corner case.
Right.
So are you going to SC22?
So I'm not going to SC22 this year. I have some personal constraints, and I think this is
Okay.
one of those rare years
Just
when I have
came
missed
up.
since like from 2006.
You going to do it virtually a little bit or something?
I think virtual has not really worked for me either. So I will just refrain from doing
You're just going to put it off completely?
it off this year.
Okay, okay. So let me ask you my big wrap question that I'm asking everybody. Assume you're talking to all of the HPC vendor community right now. What do you need from them in 3 years?
I think that's a great question. So what has really bothered me is that we I'm putting my perspective as a programmer.
Yeah.
And I usually try to work directly with domain scientists. So I'm talking to computational chemists, I'm talking to biologists, look at their core problems and see how we can pose them as graphs, and then try to bring some of our graph algorithms. So I want to minimize the time I spend on programming. I want to be able to use whatever I have done before on the next platform. And this
Makes
has not
sense.
been possible for us.
Really?
When we go from CPUs, we had to take a step back, rethink about our algorithms, highly optimized for the GPU platforms. And again, that was a little vendor specific because we optimized for whatever was available to us.
Yeah.
But that's even not easily transferable
got two
from
more.
one platform to another platform. So every time every minute I spend on trying to optimize for hardware, that's the time I'm not using to make the graph algorithms work for domain problems.
But if you, with this being a problem, then you're basically saying stick to the same hardware.
I am not saying that we should stick to the same hardware. Can we stick to something that is stable across
So you
all
want
of these?
you want a common
Yes. Common
model.
way of programming the systems so that we can minimize our time trying to optimize for different hardware platforms.
So you're kind of asking vendors to sign up for the same programming interfaces and APIs that their competitors are using.
So I don't believe I'm really asking that. So what I'm asking is that, for example, AMD is trying to build these tools where you could take code written in CUDA and put them onto the AMD platforms.
I don't know if CUDA let them do. I don't know if NVIDIA let them do it. There's some
so there are
legal,
some tools
might be some
out there.
legal issues, but maybe not.
Right. So something, anything that helps. So I think I believe it's just hardware is just one small part of it.
Good translators
Right.
would help.
Good translators would help.
And I think that, I know AMD has a translator that doesn't get probably enough publicity, but it will as they keep pushing out their GPUs. And I know Intel has one API,
Right.
not really a translator, but I think there might be some translatory stuff in there. And CUDA or NVIDIA has, CUDA. And I don't think that translates from anybody. I think that's design in CUDA. Enjoy.
Yes. Right. I think our current state is that we usually have the idea of ninja programmers to extract every last ounce of performance you have got on the hardware. I think we should step away, at least for people like me who want to spend and solve problems in the domains. At the end of the day, we are all here to accelerate science. We want to advance humanity, and computing happens to be our tool.
So, end message from you in the vendor community, can't we all just get along for the greatness of humanity?
Yes.
Good job. Well, thank you so much. I really appreciate it. This has been great. Dan Olds here. We are still on tour stop number 1 at Pacific Northwest National Labs, and I'm sitting down with Vito. Vito, introduce yourself. Tell us what you do.
Hello, I am Vito Castellana. I'm a senior scientist in the High Performance Computing Group, which I joined 10 years ago.
10 years ago?
Exactly 10 years ago.
Wow.
Yeah.
Okay.
And my background is in design automation, so I've been working on methodologies and frameworks for basically building hardware, starting from high-level specification, mostly C and C++. And since I joined the lab, I moved from the lowest level of the stack, which is the hardware, to the highest level of the stack, which are APIs.
Which is what, WordPress?
No, that would be probably out of my confidence zone. I would say that I also work now on APIs, programming languages, and things that actually interface
you moved up quite a ways.
to the user. But I still love to work in the middle. So I still work on hardware. I still work on compilers and write software as all my other colleagues.
Hardware never gets out of your blood, does it? Once you work directly with it, it can't.
It really can't, because it gives you unique understanding on the full stack. My personal belief is to write better software, you need knowledge of what's happening underneath.
Absolutely. You've got to understand that hardware resources are valuable. A lot of programming, and this is a real general statement, but a lot of programming has gotten very sloppy since we got large memory and large disk sizes and stuff like that. I mean, it's not like the old days where they would, write an assembler in order to be able to save a couple of bits and bytes here and there, right?
Absolutely.
Yeah. So what are you doing that's sexy now?
Wow, plenty of things. Again,
and I'm talking in a computational sense. Okay.
Absolutely. Yeah. Again, hardware, you can't get rid of it. I mean, it was my first love, so I still work on hardware design, and we are doing a ton of things on the design of custom accelerators.
Yeah. We talked to Kevin earlier. So are you working with that team a little bit?
A little bit. I mean, we work as a team in several projects, so probably there is some overlap there.
So what kind of custom accelerators are we talking about?
Our ultimate goal is basically to allow any developer to design their own accelerator, custom to their applications. And that is made through high-level synthesis, and I'm an active developer of high-level synthesis methodologies. I've done this for the last 15 years. And basically the idea is that you have a high-level description, and now it's becoming higher level because we want also data scientists and domain scientists to be able possibly to produce their own hardware using, for example, tools like TensorFlow.
Are we talking about, though, when it gets down to the hardware form factor level, are we talking about a personality on an FPGA?
That is one of the targets for sure.
It's pretty promising.
Historically, that has been our main target, but we are also moving towards. So our motto is democratizing hardware design, and we want to achieve that building tool chains which are open source. And this is going beyond FPGAs as targets.
We talking RISC-V type of thing?
We're talking about ASICs.
ASICs?
Yeah.
But those are expensive.
Those are very expensive, but if you look at some of the roadmaps, there are some claims about standards and tools that actually will make the process cheaper. We are not talking about $1,000. We are talking about significant expenses still, but at least we have ways.
You're probably not talking about 5 nanometers either.
We are actually pretty close to that.
Oh, really?
Because
that's where the price really jacks up.
So basically, there is a lot of community effort in trying to come up with open source methodologies, tools, and also libraries. There are some cell libraries which are available 7 nanometers.
Okay. But
historically, you are correct. We have been far away from that because in the open source community, the most technology libraries available were in the 45 nanometer scope.
Yeah.
But now there is some news. There are some tech libraries, cell libraries, 12 nanometers, 7 nanometers.
But where's your open source fab?
There's no open source fab.
I know. That's where the money's got to be spent.
Baby step. Hopefully,
Baby steps.
We are gonna get to a point where, as like 3D printers, you can just offload your design to some vendor
Some
and
machine shop somewhere, and they start, oh yeah, we can do that, and punch a few keys.
The future is pretty promising because, again, historically, also the tools were like very expensive.
True.
They were black boxes that you couldn't open, so that was a limiting factor for research.
Owned by big companies
Yes.
that were never going to let it go.
And so when it comes to open source, it's not just using the tools. It's also a matter of opening up the tools so that you can plug in your research, you can prototype ideas, and you can put your expertise in the tool so that you produce new hardware. And we have done that with several tools, actually, to basically validate our design ideas and methodologies, implement them in the tools so that we can generate hardware based on our concepts.
Very interesting. It seems like it's probably within your grasp to do this with FPGAs.
Yeah, FPGA is definitely the low-hanging fruit because it's well-established technology. They're getting bigger memory, and the tool chains are.
Then maybe the step beyond that would be RISC-V.
RISC-V, from that perspective, it's a pretty interesting approach in the sense that we can extend the ISA.
Yeah.
So attaching custom accelerators would be easier than using a conventional processor.
Again, and there's probably going to be, as it advances, more and more fabs coming out that are doing it as well.
Yeah, there are some actual processors that have been deployed. Can't go into the specifics, but I mean, there are actually ASICs, not just FPGA prototypes.
Yeah. Well, then, we're seeing some changes in computing architectures and potential architectures with things like CXL, composability, stuff like that. Is that something you're looking at?
Absolutely, because as I mentioned in the beginning, so my first love has been hardware design, and I love architectures, and that's what I do 50% of my time.
Yeah.
The other 50% of my time I spend on programming abstractions and concepts for heterogeneous computing. And this includes also how to handle diverse devices on the same machine, and to really achieve not just the best performance, but also productivity, portability of your codes, and stuff like that. You need an ecosystem, and I'm trying to build such an ecosystem using a library that we are developing here that basically allows you to program distributed systems, but as knobs to plug into more sophisticated architectures, including accelerators.
Okay, but to be able to plug into those across just different hosts is really interesting to me. To be able to pool huge amounts of memory, change the ratios of GPUs or accelerators to CPUs. So that's got to be something that gets your heart going a little bit as a hardware guy.
So absolutely, and what we really need, and this is a conversation that is going on in the community since a few years. I will simplify a little bit. What we need is a map of your system. And by map, I mean a sort of directory where we have an enumeration of the resources that you have with some characteristics of the resources that you have. Maybe, for example, GPUs, maybe CPUs, amount of memory that you have, storage,
that sort of stuff.
I/O capabilities, this kind of things. And hopefully coming with the API to access those resources. Once you have that, programming the system and taking the best of the system becomes not straightforward, but much easier.
Doable.
Yes.
Yeah, right.
And as a software library developer, I could tell you if that thing was something that existed, we could probably build a library to move seamless from one accelerator to a CPU to a GPU.
Wow.
Seamless.
That would be very, very good. Well, let me wrap up with asking you the question I'm finishing with everybody pretty much. Assuming that you're addressing all of the HPC vendor community, what do you need in 3 years? What do you want from them?
So this is an excellent question, and there is no one single answer. So
No,
I would say that better hardware is always good.
Sure.
But putting more iron on the table is not enough, because we need better hardware, bigger memory is always welcome.
More memory bandwidth.
More memory bandwidth, absolutely. More cores, all of this is good, but we also need like better software ecosystems, especially when it comes to heterogeneous computing. And I would love the vendors to come together and work on standards, because standards are the way you basically could achieve this kind of unified ecosystems. And for example, C++ has a pretty active community on that. And for example, converging on programming abstractions, that would be great, including also accelerators, GPUs, CPUs,
Whatever.
possibly FPGAs, and yeah, whatever.
You think it'll happen?
It's happening.
Okay.
But when it will finally happen, that's a pretty tough question. I hope soon. And I'm working hard to give my 2 cents to the community to make it happen.
So you're doing your part.
I'm doing my part.
Very good. Well, thank you, Vito. Really appreciate the time. We will talk to you again soon.
Thank you.
Dan Olds here, and we have yet one more interview from Pacific Northwest National Lab. It is Gokcen. Please tell us a little bit about what you do.
Okay, so I'm Gokcen Kestor. I'm a senior research scientist at PNNL in High Performance Computing Group, and I have been at the lab like over 10 years, and very long time. So I started as a postmaster. Then I moved to postdoc. Since 2014, I have been a research scientist at the lab. And over the 10 years, of course, I work on different research topics. So I start to work on the performance modeling, performance power modeling, and I look at on the task-based programming models. But the last 3 to 4 years, mainly I'm focusing on the compiler and runtime optimizations for
compilers.
Yes, and for heterogeneous platforms. So and looking at the problems that how we can address performance portability across these heterogeneous systems.
Okay, so how heterogeneous are we talking about? You're probably talking about more than just the standard GPUs,
yes,
right?
Definitely. Like we have been, like, of course, like as I say, we need to include the traditional hardware, CPUs, GPUs, but we are looking at beyond that, and like we are looking at the FPGA platforms, and also now I'm sure you are very familiar with the hot topic AI and machine learning. So we are looking at the AI accelerators. So, and this is like
there are a whole bunch of different AI accelerators, right? A lot of them with names that we would not be familiar with.
Yes, there are so many startups that are working on. There are some particulars. One at the lab, we have the hardware in-house that we are working with this kind of accelerators. But my research topic mainly looking at not the how we of course there's a part that we are looking at how we can co-design the hardware accelerators for the specific applications, but in the main I'm looking at how the programmer, like the domain scientist, that's like mainly in the area of chemistry and data analytics, how the domain scientists can write their application in a high-level representation. You can see that the formulas on their whiteboard, and how we can run this application on heterogeneous platform efficiently. So
Without them having to be programmers.
exactly,
right?
like without making them like they shouldn't worry about how can they accelerate their application on this underlying system. They shouldn't worry about that. They should focus on their science and writing their application in a way that they are familiar with. Like we don't want also them to learn all type of different programming.
They don't have to learn CUDA. They don't have to learn
Exactly.
about the MI250. They don't have to learn
Exactly.
about Ponte Vecchio.
And like what will happen next time, another hardware platform will come out. Vendor will provide their programming models. We don't want them to also rewrite their application for a specific programming model. We want compiler to take care of this, mapping the application to the heterogeneous platform.
So the compiler is going to be the translator, the universal translator.
Yes, actually, we call it even unify intermediate representation because it's the unify across different application domain, across different heterogeneous platform. You can think about something in the middle.
That needs to be a really complex compiler then.
But this always the compiler research is not trivial because as I say a lot of also software development you need to make it applicable, right, to be useful for the scientists.
Interesting, very interesting. And wow, that is a big job.
Several people is working in our team on this project, and
how's it coming along?
actually so far like I told you we got some funding for the last 3 years, and this is still is a research tool, I will call, not development, but it is used across different application domain, and we are even showing very promising result on interesting architecture. So I think it's promising, and we are hoping that it will keep working on this. Eventually we'll get the maybe more production level.
So in looking out at the vast array of, last time I looked was probably 2-3 years ago, and I counted 50 different startups with a different type of idea for acceleration or an AI accelerator. And I stopped counting at 50 because I got tired or I got distracted. But there have to be more, even more now. How hard is it to pick which ones to work with?
So this is actually a very good question, and even if it lead to
It's a
next
great
question
question.
that how even if we as you say, depends on your application. What is the best accelerator we should pick up, right? Because there are so many, and your application requirements are different. So for this, we are doing a lot of research to understand the application requirement. What are the accelerator out that can fit? Even one step further, maybe there is some accelerator outside, they are not good enough for our applications that can be co-design new accelerators. So for this, there are a lot of application characterization we are doing, and we are looking at what are the requirements for the application, what are the existing architecture. Then we make the evaluation of the application on this specific architecture. We identify the bottlenecks, what are the limitations. So it's actually makes us move to the next step, that what is our ideal accelerator should be designed.
Yeah, and what application areas are you looking at?
So in my research, mainly I'm looking at the computational chemistry and the
Okay.
graph analytics. So there are two application domains that
So
I'm
you know our friend Vito then,
Yes, of course.
and you of course know our friend, the Mr.
Yes.
Graph, of course,
Of course.
from an earlier interview,
It's like, of course.
who's also in the room with us. But so computational chemistry and graph, those are two very
Application,
difficult
yes.
application areas. And is that going to remain your focus, or will it be expanded over time?
So at least the last 3-4 years, there are main application domains, but also thinking the mission application at PNNL, computational chemistry, graph algorithms, there are main application domains. So I believe I will keep working, but also I am looking at also other application domains that I can leverage our compiler.
Okay.
So it is like I'm saying that still computational chemistry graph most probably will be my main application domains, but also looking at around that, is there any way that we can generalize our compiler, extend our compiler to other application domains as well?
Because I could see some great usability for this in other domains as well. If you've done kind of the hard part of having the hardware definitions in there, in the compiler, a little bit easier to extend it out into other application areas, I would think.
Yes, like I can give you an example. When we start working on our domain-specific compiler that I'm referring, we mainly focus on computational chemistry. It's what we start, and we look at in WChem different computational chemistry methods, how domain scientists, they are writing their application in the very simple, like tensor algebra style, like the Einstein notation you will see on the whiteboard. Then when we wanted to move to the next step, we moved to the graph algorithms. As you say, it wasn't completely applicable, but it allows us to, with a like little step, to move to the next. Because however you put it, there are some common operations across different application domains, so they can be reused. Maybe some application domain, they have their specific operation requirement that we can build on top.
Are you working with the HPC industry, with the folks that are building the accelerators? Are they cooperating?
Actually, yes, we do. We are working some of the accelerator, like maybe I can give a name like the Sambanova and Xilinx. They are main our collaborators right now.
Okay.
We are looking at their AI engines, that how we can write our computational chemistry methods on these emerging architectures.
Now, are you going to SC22?
Yes, I'm going like in person also.
Excellent. What are you looking forward to seeing there? Anything special?
So, I'm pretty excited this year because like after 3 years, the last time I was there, it was 2019, and now I'm excited about meet with my colleagues and have the discussion, being in this environment, hearing a lot of interesting talks and panels. This makes me excited, and also I am involved in several activities. I'm organizing a couple of workshops, and I'm involved in the panel. So this makes me excited also how things will actually go back to normal.
Yes, that's what we're all looking for in that. Now let me give you the big wrap-up question. I've been asking everybody. Assume that in this video you're addressing the entire HPC community of vendors. What is it that you need from them, say in the next 3 years or after 3 years? What can they do to make your life easier?
Make my life easier.
Make you happier.
It's a really hard question. So what I will say, I think applications people, domain scientists, and the compiler designers, and also architectures, we should work together. I think this would be very important for us to be able to move forward. And like if we shouldn't just focus on our single domain like what we are doing, and without knowing that what are the, like I'm giving application requirement when we do the hardware design. So we should talk to each other, and because of that we keep using the word like the co-design. I think very important in this aspect. We should work together to advance the science.
Excellent. Great note to stop on. Well, thank you so much. I appreciate it.
Thank you so much for the opportunity.
500 miles of open road, and I'm driving down the highway.